Hi, I'm Lowell Gentry. I'm a research agronomist. I'm looking at ways of trying to keep nitrate in the field, keep it from moving from fields to streams. And tile drainage is an essential tool for farmers in central Illinois. With our very flat, rich mollisols, poorly drained, we need the tile drainage for our ability to get into fields when we want to, and it helps with crop productivity. Today I'm going to talk about a long-term data set that we have. It's a river data set with nitrate concentrations that we have had for over 30 years going. And in fact, I took the very first sample back on June 14th, 1993. Our research group has been to this site 1,740 times in the last 30 years. And so we have an excellent document to see if we're moving the needle at all as far as improving water quality and reducing nitrate runoff. In 2015, the Illinois Department of Agriculture and the Illinois Environmental Protection Agency got together and they developed the Illinois Nutrient Loss Reduction Strategy, which contains a suite of best management practices for farmers. And it has established this goal of reducing nitrogen and phosphorus loading to rivers by 45% by the year 2035. Now there is an interim date where the goal is to reduce nitrate in streams by 15% and phosphorus by 25%, which is fast approaching. This long-term data set is on the Embarras River, and the USGS gauges the river at Camargo, Illinois, and so that designates the Upper Embarras River watershed. It's 119,000 acres. It's 90% row crop agriculture, and there's very little sewage effluent that goes into it and very little livestock on the land. And so it's an excellent watershed to look at the impact of row crop agriculture on river nitrate. This is a graph of our 1,740 water samples that we've collected for nitrate concentration in the Upper Embarras River. And what you can see is that every year the nitrate concentration goes up in the spring and then it comes back down in the fall, generally below 1 part per million in September and October. Well, this is when tiles are not flowing, and so it was quite obvious to us early on that tiles were the conveyor of nitrate from fields to streams. What you can also see here is that in 1993 the nitrate stayed up all summer long, and that's because it's the wettest year on record and tiles never stopped flowing that summer. So we started out with the outlier, but the next 29 years tiles stopped flowing during the summer and nitrate went down to below 1 part per million. I would point out that the highest concentrations were in the spring of 2013 following the severe summer drought of 2012. So over the last 30 years we can regress river flow versus river load for nitrogen. And we see an extremely good regression, which makes sense because flow is part of the equation for load. But nonetheless, what we find is that we've averaged about 13 inches of runoff each year. Now let me explain what inches of runoff is. That's if we took the entire annual flow of the river and spread it out over the 119,000 acres in the watershed, and we determine how deep that would be. And so we get about 39 inches of rain a year at this latitude, and a third of that becomes river flow. And so using the regression line, we can come up from that 13 inches of river flow up to the line and then over to the y-axis, and which would then predict that our mean nitrate load per year is about 27 pounds per acre loss. Now, in a wet year we can lose as much as 50 pounds per acre, but in a dry year like the summer of 2012, we only lost 8 pounds per acre. So that's the kind of range we see over the last 30 years, with an average of 27 pounds per acre per year loss. Now, there's 2 points, or 2 years, that fall off the regression line by more than 30%. And we can explain why those points aren't closer to the line. One is that in 2010, we experienced the lowest flow-weighted mean nitrate concentration out of all 30 years. And that's because in 2009 it was a very wet fall and very little nitrogen was applied that fall. And it's quite apparent to us and through other studies that fall nitrogen is a part of our river nitrate load problems. In fact, we've found that fall N can contribute as much as 30 to 35% more nitrate to the tiles. And the other year that falls off the line, but it's above the line, is the year after the drought. So there was lots of unused fertilizer in the fields after the 2012 harvest, and then 2013 being a very wet January through June, and we find that the load was 30% above the regression line. This graph shows the annual flow-weighted mean nitrate concentration in the Upper Embarras River over the past 30 years. And again, as I've mentioned, 2012 was a drought, and so 2013 has the highest flow-weighted mean at 11.6 part per million, where the year without the fall N application, or the year after the fall N application, we had the lowest flow-weighted mean of nitrate concentration at 5.7. The good news is that when we put a trend line through this data set, we see that nitrate concentration is going down over time. In fact, it appears that we have come down about 18% since the beginning. We've come down from about 9.6 part per million down to 7.8. And that suggests that we are seeing an improvement in water quality in regard to nitrate loss. And I believe that's because we've had so many good years in a row with excellent crop yield and good nitrogen uptake, and the field nitrogen balances have improved, and now the rivers are showing it. Now, this video was brought to you to set the stage for what are the current conditions for river nitrate loss in these intensively drained watersheds in central Illinois. So stay tuned for more videos that look at other conservation practices to reduce nitrate loss from fields to streams and yet maintain yield and profitability.